Using DDL. Before we go any further, let me say that DDL is a subset of the SQL command set that stands for Data Definition Language. Just wanted to get that out of the way. I'm pretty sure I defined DDL earlier in the course, but certainly by the end of this nugget, you'll understand exactly what it means. We're going to begin the content of this nugget by examining the main database objects. In other words, giving formal treatment to constructs like tables, views, indexes, sequences, directories, and so forth. We cover a lot of these concepts in a much greater degree of depth in my CBT Nuggets course for OCA DBA1, but as a value add, I wanted to add it to the SQL Fundamentals 1 simply because it is a fundamental topic. We're going to spend the lion's share of our work in this nugget in learning how to create and manage tables. Tables form the fundamental data store in our database. We've been using tables in every nugget so far in the course, but by the end of this particular nugget, you'll know how to manipulate tables themselves. In discussing tables, this is going to involve understanding data types as well as constraints. Yet again, this is a topic we've flirted around with quite a bit thus far. We're now going to take our time and formally understand it. Let's get to work. The main database objects. Although of course our subject matter for this course is Oracle Database 11g, the objects that you see on this whiteboard are really generic objects that will be a part of any major relational database management system. Frankly, even a desktop database engine like Microsoft Access 2010 is going to have the lion's share of these objects. As I said, they're very generic to relational databases. Of them all, I would say that the table is the most fundamental because, as I said in the previous whiteboard, that the table is the fundamental data store for your database. At the lowest level, when you're adding new records to a table, this is in fact where they're stored. Thus, designing your database and establishing normalization rules are always going to involve those fundamental building blocks called tables. So as a database developer, you always want to be thinking about how best to design your tables to avoid redundancy, increase security, and maximize performance. Now, views are sometimes called virtual tables. Now, what does that mean? Virtual means that it's a view or a window into one or more tables, but it doesn't exist as a data object itself. Now, it's true that with Oracle and other relational systems, you can manifest data inside a view, but for our purposes in this nugget, consider a view to be a window, basically just a SQL statement that aggregates rows and columns from one or more tables. Really, a view could be considered also a stored select statement. And when you query the view in exactly the same way that you query a table. You're not interacting in the view itself, but you're instead working through the view that's giving you a filtered look into the fundamental data that's stored in one or more base tables. A common principle of database design is that we want to keep our database users far, far away from our base tables. Really, the only folks who should be touching your base tables directly are database administrators, database developers, and perhaps the operating system itself. For our users, we want to put them through views wherever possible to filter what they're seeing in those base tables and also to hide complexity, to hide data that just through security, for security reasons, we may not want our users to see. For instance, we might have employee data in our base tables that stores very sensitive information, including things like social security numbers. If we need human resources workers to have, say, a read-only view of that employee data, we can create a view for them such that when they query the view, it pulls only a subset of columns, definitely not including the social security number column for those users, you see? Therefore, views are the workhorse for database developers. They're a way to hide complexity, increase security, and keep those end users away from your base tables. Indexes are a really good idea to improve lookup performance in your tables. We'll be working with both views and indexes in the next couple of nuggets, so I won't say an awful lot about indexes right now, other than you can create them for a table to improve data access speed when you're looking up records within those tables. A sequence is nothing more than an auto number schema. Auto number is kind of a Microsoft term. If you've used Microsoft Access Database, they have a data type called auto number that functions similarly to the Oracle database sequence. Oracle stores these sequences as separate objects though. Now a sequence allows you to determine how you're going to generate unique numbers. That is to say, we could create a sequence that starts with 1 and then proceeds one integer at a time to infinity. We can start with 100 and use an interval of 10. You see what I'm saying? Therefore, sequences are especially handy for data fields, in other words, column data in a table that needs to be unique, in particular for ID fields that are going to serve as primary keys for each record in that table. A synonym is simply an alternate name for a database object. Again, when you're developing your table layout and you're building views on top of those tables to hide complexity, synonyms are another way to hide complexity and make it easier for your users, your customers, whoever, to interact with those objects. You may have views even that have really cryptic names. If you're new to IT and you do get to become a DBA and start working with database developers, you'll find that oftentimes these developers name their tables and even their views in the most cryptic way, such that just looking at the object name, you would have no idea what it does. So you may have a view that pulls some employee records like we talked about earlier, but for some reason it's called XYZ in Oracle. We can create a synonym for that view and call it emp and then deploy that as a synonym such that when users query emp, they're actually querying the XYZ view. Similar idea to symbolic links in Linux or Mac OS X, shortcuts in Windows. It's just an alternate way to access the same piece of data. Triggers are really excellent objects. These are done in procedural SQL, which if you've been watching these nuggets sequentially, you should know a couple things about, that will execute on particular DML operations. We can use triggers to take care of auditing issues. We can use them for security purposes, for increasing data integrity. Really great technology to have in your tool belt as you're deploying tables, views, etc. Finally, procedure, we already know about this. This is a program that's written in PL/SQL. The generic term stored procedure can refer to a procedure itself or a function, which is a special kind of procedure that returns one or more values. We discussed this in our earlier nugget on PL/SQL. There are a few more database objects in Oracle Database 11g, but the ones on this whiteboard suffice for now. Table types. Because I think I've hammered home how fundamental and important tables are to any relational database system, but in particular Oracle Database 11g, it should make sense that we have more than one table type from which to choose in Oracle Database 11g. Now, of these four table types, the one we're going to focus on in this nugget is the standard table. This is just your ordinary database table that you would create in 99% of the time, and this is an object that once created will persist. That is to say, the table definition is stored permanently in the data dictionary, and any rows that you add to that table are in fact stored in a table space in a data file and so forth. That's really it, just a generic garden variety table. Now, as a database developer, you may have use periodically to use a temporary table. A temporary table is similar to a temporary file. It's in this case, a table that's instantiated for only a short period of time. You're not going to keep a record of the table in the data dictionary that'll survive server restarts. You're using it maybe for a bulk load operation just to temporarily store data. You may also use temporary tables as you're making tests, as you're testing various maybe PL/SQL packages or script files. All you need to know for your exam regarding temporary tables is that temporary nature can exist in the context of a single SQL transaction, or you can instantiate a temporary table that exists or persists through that session. Now, tables can be accessible or are visible, potentially visible, to any connected user. In fact, the create statement is create global temporary table. And then depending upon whether you add the clause on commit preserve rows or on commit delete rows, that will determine the scope of that temporary table, whether it disappears after the current transaction is committed or only after your session ends when you disconnect from the server. The third table type is called the external table. And again, to give a shout out to my CBT Nuggets training course on OCA DBA1, we talk about and work with and demo external tables pretty heavily there. This gives you as a database administrator flexibility, especially when you're performing what are called ETL or extract, transform, and load situations. In other words, you have a directory somewhere in a file system. It could be on the database server itself, but it could just as likely be on another box. And Oracle can actually read data from that external directory. You create an object in Oracle database to represent that external directory, and then you can grab data from a delimited text file stored in there. So the table structure, the schema of the table, the definition of its column names and data types exists in Oracle in the data dictionary, but the data itself resides outside of the database on the remote file system. Again, that's called an external table, and you may have good business reasons for working that way. In particular, with extract, transform, and load, you may have a business partner that periodically, maybe every night, will FTP a new copy of the file or an appended copy of the file to this file directory, and then your users in Oracle can query that new data by using that external table link. The fourth type of table in Oracle Database 11g is called an index organized table, shortened to IOT. An IOT is a very similar concept to the clustered index idea in SQL Server. If you have any experience with Microsoft SQL Server, when you create a clustered index, almost always that's going to be on the field that's attached to the primary key constraint. The clustered index will actually order the rows in the data file in order according to the primary key field. That's what an index organized table does as well. It makes it a lot faster to look up rows in which queries pull on the primary key value specifically. Final point about IOTs is that you want to use this table type when the primary key comprises almost all of the columns in a table. For instance, you might have a commonly accessed table that displays, or should I say stores, all of the states in the United States. So you would have your ID column that is where the organization of the rows in the data file physically comes from in the IOT, and then your second and final column may be the state. New York, Arizona, etc. Probably be alphabetized, but maybe not. Before we get to creating tables, one final bit of very important information we need to review is the concept of the data type. Again, this is one of those subjects that we flirted around with a little bit when we discussed PL/SQL and variables, substitution variables, etc. But data types are something that you absolutely must know, not only for your exam, but for your real-world success as a DBA. Remember, a data type defines, well, the type of data that's allowed in a column or field in a table. And actually, let me step outside of this just for a second and make sure we have our vocabulary down. A table, as I'm sure you know, can be looked at or examined graphically as a grid, right? Where we have columns that define the attributes that you're tracking in a particular table. The aforementioned ID would serve as a key column. Maybe in an employee table you have a first name column, a last name column, etc. Sometimes there's confusion in terms of the difference between field and column. Depending upon which vendor you're reading, whether it's Oracle's literature or Microsoft's literature or IBM's literature, you might see slightly different definitions. For our purposes, let's just look at them as essentially synonyms. Technically, some folks say, no, the field refers to the specific data points within a column, and the column refers to all of the data within that column. That, again, turns into, for me, a cerebral rat trap. Just know that your fields or your columns define your attributes, or if you really want to go old school with your database nomenclature, the domains of data that you're tracking. Now, horizontally, we have rows or records. Again, you can fight with people in terms of defining or trying to distinguish a record from the row. You could say the record refers to all the data points for a specific key value, and the row is maybe more generic. You think of the set-based results that you get from a DML statement like select. Not going to go there. We're just going to look at these as essentially synonyms, that a row or a record refers to a single unique entity within a table. Now then, I mentioned that these fields or columns are used to track different attributes that you're tracking in the table. This is where the data type helps us in terms of data integrity as well as performance. You want to think when you're designing your tables, what do I want to track for an employee's table? How can I avoid redundancy? But leaving aside the redundancy question right now, you need to think, okay, if we want first name and last name and address and phone number and employee ID, all that's well and good, but we also need to determine and map a data type each one of those field names or column names. The good news is you don't have all that many to choose from, practically speaking. The ones you see on this whiteboard are going to comprise the vast majority of data types that you'll use in your tables. It just isn't that complicated. There are some numbers that you should keep in mind. It's what I call the 30-30 rule. This is going to be, of course, all specific to Oracle Database 11g. When you're naming your tables, you have 30 characters max to deal with. No spaces. You want to be careful in how you're choosing those names. You want them to be intuitive. But again, no spaces. You can use underscore characters, but no other funky alphanumeric characters. The other 30 in my little 30-30 rule here refers to column names. Again, you have 30 characters max for your column names. Shorter is better, but you don't want to get too cryptic. No spaces is the main rule. You can use underscore if you really need a separation or a separator between different words or clauses. All right, first data type variety we'll look at are the character-based data types, and those are, the main ones anyway, varchar2, char, and clob. The main difference between varchar and char is that the varchar is a variable length character field. In other words, if we create a column that uses varchar 220 and we have up to 20 characters of space allotted for each data point or each row underneath that column. And you tend to get a space savings with varchar because it doesn't pad characters. That is, if we have a first name column that's defined as varchar 220 and the last name is Smith, 1, 2, 3, 4, 5, that's 5 characters. The other 15 are just released. They're not even used. Therefore, many DBAs will use varchar 2 almost exclusively for alphanumeric character data. Now, char, on the other hand, is a fixed length character string, such that if we define char20 for last name and we put in Smith for our first row, then it's going to put in the 5 characters or 5 bytes for SMITH and then pad out the remaining 15 characters so that you are in fact always storing 20 bytes worth of data or 20 characters worth of data for every row. So you might think, well, gee, that doesn't sound smart. Why wouldn't we always use varchar instead of char? Well, we can get into this if you want to. We don't have the time to go really deep, but there are some performance implications, and this is a little controversial. You can get into arguments about this too, that by using character-based data types carefully for fields where you know in advance that you won't need any more than X number of characters, you're saving space and you're mildly improving the performance of your system. That's all I'll say about that now. A good instance of using char would be maybe a state column. If you're tracking US states that have just 2 characters, as you know, it would behoove us to use char2 for that particular data type. Fixed length char columns can have a maximum length of 2,000 bytes, also equivalent to 2,000 characters. Varchar 2, 4,000 bytes, or 4,000 characters. The third character data type is called CLOB. This stands for Character Large Object Data. This stores up to 4 gigabytes of not binary. We're not talking pictures or movies or audio files, but just plain old garden variety alphanumeric ASCII or Unicode text. You could store resume, raw data in here, essays, whatever the case may be. CLOB is a good candidate for larger data points. Moving on, numeric data types. There's quite a few to choose from. Date and timestamp. Pretty self-explanatory except for the formatting on those, which can get hairy. We'll cover that just a little bit in the demo in this course and later on in the course. BLOB stands for binary large object, and this is where we get large size binary storage. If we had an employee database and we were actually going to store a bitmap image, a photograph, so to speak, of each employee in the table, you would would attach or use the blob data type for that. You have the traditional number data type. You don't have a differentiation between float and all of these others that you have in SQL Server and MySQL. Here we can just be satisfied with number. And then you have precision and scale, x comma y. What precision and scale means, the first number is how many digits are allowed across the board on either side of a decimal point. The second is the scale, and that refers to the number of digits allowed to the right of the decimal point. Therefore, if we create a column that's number 5, 2, then that's going to support by default numbers from negative 99,999, negative 999.99 to positive 999.99. You see how that works? Final point I'll say about data types before we learn how to use the create table statement is when to use number versus, say, varchar2. And I mentioned this earlier in the course, but it bears repeating again. The decider for you is whether or not you're going to do operations or expressions on that data. For a zip code column, you would absolutely choose varchar or even char for that. More likely char, since zip is a fixed length number in the USA. Credit card numbers, again, you're not going to crunch those. Salary, absolutely, that would be number. Sales commission percentage, that's another number. So just use your head, ask yourself, am I going to do an expression with this column? And if the answer is yes, you may indeed always want to go to number. Well, finally, we come to creating tables, how to do it. Well, shorthand notation, generally speaking, how this is taught is that there are three chief data definition language, or DDL, statements in SQL. There's the one we're learning right now, which is create. There's alter, which is what we use to make structural changes to an object. And then, as we'll learn in a couple minutes, there's drop to remove that object. Now, what we've been using thus far almost exclusively is the select DML statement. Data manipulation refers to acting upon objects that have already been created. What we're doing now is a fundamental shift because we're actually creating new objects that can then accept DML as long as the security is set. We're going to deal with security in yet a later nugget in this course. So create is our generic DDL statement, and to create a table, yes, we use create table. The basic syntax works like this, friends. It's create table and then the name of your table, maximum of 30 characters, no spaces. And then after that name, we have opening and closing parentheses in which we have our column declarations. And the column declarations consist of the column name, space, and then the data type. Pretty straightforward. The columns are separated with a standard issue comma, and remember that SQL ignores white space. So I could put this opening paren down here if I wanted to. It doesn't matter. I'm just by habit used to putting it right after my table name. You can put the columns on separate rows. I like to do that for easier legibility, but you just as well can run them all together. Remember, that doesn't matter. But what does matter is that we need our statement terminator at the end. And as long as we have the privilege to create objects, create tables in particular, in Oracle, then this would work all day long, and we would then have an empty table called tab 1. If you then wanted to add an additional column to the table, yes, we would use alter table tab 1 and then make our change. And that's really how it goes. This is the most basic formulation imaginable for creating tables. Oracle gives us a lot of flexibility. I would encourage you read the create table syntax document in the Oracle documentation and get a feel for how it works. You're also going to see on our upcoming demo that I'm going to show you how to build tables using the SQL Developer tool. And don't poo-poo that, friends. I know that some of you who may have some previous experience with Oracle do not trust graphical tools, but for those who are using the tool as a learning agent, if for no other reason, I think you're going to like it because we can use the graphical tools to lay out the table, including things like constraints that can be kind of tricky to write, just keyboard based. And then we can have SQL Developer show us the code behind what we did in the graphical user interface. So again, as a learning tool, this really can't be beat. Now, we spend all this time building tables, 1, 2, 3, whatever those tables are, to track various elements within a single database. What can we do to protect those tables against the all-powerful, all-pervasive problem of human error? If you have people doing data entry in into those tables, you're bound to eventually run into human error. Things like typographical errors, maybe a user typing an O instead of a 0, simple things like that. But these little problems can wreak havoc in your database over time. And when your business is reliant upon that database to do business and to generate money, moreover, if that database is under federal strictures with accounting laws like Sarbanes-Oxley or HIPAA in the medical world, these errors can be very, very costly. So we really need to make sure at all costs that the data that is being added to our tables is correct to the best of our knowledge. Now, the first way to assure this is to choose the correct data types. That is to say, if we create a salary column in an employee table using the number data type, then we're going to have a problem. Actually, Oracle will have a problem with it and not let you do it if you typed foobar in that column instead of an actual numeric value. So selecting the proper data types is rule 1 to make sure you get correct data put in each column. The second thing that you can do that any relational database worth its salt will allow are the creation of integrity constraints. And you can add these or attach these constraints to columns in your table either inline in your create table statement, or you can do it at the end, at the table level as it's called. Doesn't matter to me at all. You need to understand that there are these two types such that you'll recognize what's going on immediately when you see SQL on your exam and when you're seeing real life table definitions in your experience. The 6 integrity constraints that you need to know are the ones that you see in this list here. Now, we've been talking about primary keys, their purpose of keeping your rows in your table unique. Primary key is instantiated or attached to a specific column using the primary key keyword. Not all that difficult. The toughest part is your planning stage where you're designing your database and determining where the primary key is going to be. Remember that the element that glues more than one table together is the primary key on the one side of the relationship and a matching column appearing in another table to which we apply the foreign key constraint. Now, there's not a foreign key constraint keyword in Oracle. Instead, you use the keyword references. More on that in the upcoming demo. So this is your coupling of statements that you need to create a table relationship in Oracle Database 11g. Unique forces uniqueness within that column. Now, you might immediately think, at least I hope you are, well, Tim, what's the difference then between a primary key constraint and a unique constraint? They both enforce uniqueness, don't they? Well, yes, but really the only thing that differentiates the unique constraint from primary key is that you can have one and only one row that has null for its value. Primary key will never allow null values. It's just by design. So you attach the unique constraint to a column that does in fact require uniqueness, and you have the possibility of one and only one null. Of course, the answer to the question, well, why can't you have more than one null in a column, is, well, that would violate the uniqueness rule, wouldn't it? Not null is the only integrity constraint that you can't add at the tail end of your create table or alter table statement. You have to attach this in line when you're declaring your columns, and this just says you have to have some data. When you're doing data entry, that particular column must contain data. It can't be left open. Default is a nice way to make data entry easier on your users. This provides a default value. Maybe you can set a default value where state equals New York when the vast majority of your customers are in fact in New York. That should make data entry go much faster, or at least marginally faster in this case. Finally, the check constraint is perhaps the most complex of these 6 integrity constraints because it involves us with expressions again. Check is where you can have Oracle check an expression prior to allowing a value to go into a specific column. Maybe you have a salary ladder in your organization such that your salaries, the lowest one is $25,000 and your highest salary is $100,000. That's just by organizational mandate. Well, you can create a check constraint that ensures numeric values going into that column fall within that range of 25,000 to 100,000. That is to say, if a data entry clerk happened to enter 24,000, the check constraint would prevent that data from going into the table. You see what I mean? So check gives us as database developers quite a bit of flexibility in ensuring integrity in our tables. Finally, you can provide names for your integrity constraints. This is a good way to keep them organized and just to be a good steward of your database. After all, you may not be working for your organization forever. In fact, nobody does. And you want to do what you can, it seems to me, to make your replacement's job as easy as possible in understanding what's going on in terms of table structure and constraint usage. Before we go into our demonstration, let's round up some table operations. This is a smorgasbord of different table-related commands, statements that you should be aware of. First, we have the create table as select statement. This can be used for testing purposes and also good just to quickly clone or cloning tables. What you're doing here is creating a table based on the results of a select statement. So if you select 3 columns from some other table within that database, your create table will automatically define those 3 columns with the data types that they were used and then populate the rows with, as I said, the results of the select. This is going to be excellent in a testing environment. If you don't want to do something to the source table, you can quickly essentially clone a subset or all of that table to another object and work on it. Rename table is what you would do to, well, rename a table. We want to be really careful with renaming objects, not only in Oracle, but any relational database system, because of the D word, dependencies. You may have, or your colleagues may have, PL/SQL code modules, views, etc. that include hard-coded references to your tables. When you use rename table to rename a table, it doesn't mess up permissions at all. You don't have to reassign permissions, but it's going to render invalid any views or PL/SQL stuff that have those names hard-coded. So you can fix that. You can recompile the invalid views, and Oracle will go out and resolve that name problem. But it's just something to be careful of. Best to get the name correct on the first try. Finally, we have truncate table and drop table. Remember that the triad of DDL statements is create, alter, and drop. We don't say delete table, we say drop table. Drop is just an SQL standard. Drop table will nuke the table and its rows. Very, very powerful. We want to be careful of that. The good news is that in Oracle Database 11g, you can enable a feature called flashback that essentially when you drop a table or drop an object, it goes into a recycle bin. And as long as you can retrieve that using flashback prior to when the recycle bin is purged, you can actually undo some pretty potentially or otherwise catastrophic changes. Truncate table is different from drop. Many folks get confused between these two, but don't be. Whereas drop nukes the table structure and its data, truncate table will only clear out the contents of the table. It will nuke all the rows, but then the table itself would have no rows if you ran a select star against it, but its structure would still stand. And there are some additional clauses you can add to determine what happens to the space that used to store those rows that you just truncated. In this demonstration, we're going to work with creating and dropping tables. You see, as promised, we're in SQL Developer. I have my connections window open and docked, and I'm connected to the HR schema. I've showed you this before, so this isn't anything really surprising. What you see are all of the objects within the table. I would have to be logged in as sys to have access to everything, of course, but just taking a look at what we have in this list here: tables, views, indexes, packages, procedures, functions, triggers, sequences, materialized views. Remember I mentioned that a view is ordinarily simply a stored query that doesn't have any data attached to it specifically. You can materialize views that in effect duplicate table data for increased lookup speed. Directories, etc. So we have our objects. Of course, the base of everything are our tables, and the view here filters on tables that we own. In other words, tables within our schema. We're going to talk in more detail about privileges and security later in the course. All this is pretty straightforward stuff. At least these top 7 are the ones that come standard with the HR schema. When you select a table, we see the describe show up by default, and then we can move our way over to look at constraints, where it gives you exactly what's going on, the name of the constraint, the type of constraint, etc. Or we can right click and select edit from the shortcut menu to actually bring up the edit table dialog box. That gives us columns, primary key, and then different constraint types. You can simply select to filter your view, and then it shows you exactly what's going on with that table. And it's telling us, first of all, we have our types of tables, that in the HR schema, the countries table is in fact an index-oriented table, and it has a primary key called country CID PK that is matched to the country ID column. Foreign keys means that we do in fact have a many-to-one, if we're working backwards from countries, relationship between the countries table and the regions table. So you're going to see how this works on the create side right now, as a matter of fact, because to create a table is as easy, in SQL Developer that is right-clicking the tables node and selecting new table from the shortcut menu. Depending upon our permission, we can assign the table to a specific schema. HR is a fairly low privileged account. It pretty much has the ability to create objects within its own schema, but I'm not going to be able to tuck this new table in anybody else's schema. You notice the drop-down box doesn't allow it. If I were logged on as the sys super user, I could tuck this table wherever I wanted to. I'm going to call this category, and I'm going to use uppercase here. The names are stored, table names and column names are stored in uppercase by default by Oracle. I'm just going to use upper for grins here. Now the simple view is what you see by default in this dialog box. You notice the advanced that we're going to tick in just a second shows us two tabs, table and DDL, and it gives us a default first column called col1 varchar 20, and then we can specify whether or not we're allowing nulls and whether this is the primary key. You can double left click in here to change those data points. I'm going to call this actually cat_ID. I'm going to change the data type. You notice it gives me a nice handy drop down here. I guess I'll keep it varchar. Remember, we're not going to do operations on the ID column necessarily. Actually, we might. So why don't I make this a number, and we'll make it a whole integer, 4 characters wide. We will specify not null, and we will apply the primary key constraint to this column. Let's add an additional column, and we'll call this category name. And again, we'll keep varchar 20 here. Also, we'll require not null. Now, I mentioned to you earlier that the SQL Developer is a great learning tool, and that comes into the forefront right now, as you see, because if we come over to the DDL tab, we can see exactly what we would need to type, or what we can type if we wanted to write this out using SQL statements. So we're saying create table category, and then between the outer parentheses, we're doing our column names, cat ID, number. If you're doing integers with no decimal places, you could just do 4 in parentheses, or you could be formal and do 4, 0, not null, cat name, varchar 20, not null, comma, and then this SQL that SQL Developer gives us is showing us really a combination of the two ways to do constraints. Not null has to be in line after each column. The other ones can either be in line or they can be at the end, like here. After your last column declaration, you would simply do comma and then write out your constraints. So in this case, the SQL says constraint category underscore PK. It gave us that name by default, primary key. And then the primary key is cat underscore ID. That's that column, you see? So let's hit advanced and see how things shake out that way. It's just the same starting data. The columns, you can add additional columns here if you want to. Remove columns the same way, and then over on the right, decide in terms of your metadata, your data type. You can also provide default values. I'm going to add a default category name of cat1. You can really be jiggy with it and add comments to your columns if you want to. And I'll do the same thing for cat ID. Have to put cat1 in single quotes because it's a string. And notice, because I'm creating the table, I can specify the table type, whether it's normal, external, indexed, organized, temporary, transaction level, or temporary session level. Primary key is already filled in because we created it. Unique constraints, we simply add them. Foreign keys, we're not worried about yet. Check constraints if we need them. This is going to be a very simple table, so I'll just simply click OK right now and deploy the table. There it is, category. If we have that table selected and we select the Data tab in SQL Developer, we can use the Insert Row command to actually do data entry and press Enter when you're finished, etc. This is dummy data, of course, but you get the right idea. We're going to work with DML, in particular the insert statement, later in the course, but it's nice to be able to see this, isn't it? In SQL Developer, on an already existing table, as long as you have it selected in the Connections tab, you can come over to the SQL tab and see the full DDL statement that defines the object. Notice that HR is our schema name, so that's prepended to the table name. It gives us literally everything, including default information regarding how data is stored, how segments are allocated, min extents, max extents, which table space the table is associated with. So if we wanted to make a change to some of this storage metadata, all we would have to do really is copy out this code into a new query window, substitute alter instead of create, and then make the changes where we need to. You see? SQL can be extremely fast in that regard. Let's create one more table now that'll be related to our category table. Alrighty, I've fast forwarded for a moment here. I've created a second table called NewProds that contains 3 columns. The first one is called ID, that's number, precision 5, scale 0, and this is our primary key column. Let's verify that. Just add that in really quickly. Come back to columns. We have a prod name column that's varchar 20, price, that's number, that's going to be a numeric field, obviously, and we're going to add one more column in that will be our foreign key constraint. Now, we're going to have a one-to-many relationship. In NewProds, in our products table, we're going to want to track a category. So we want to link out to our cat ID column. I'm going to name it the same on the foreign side of the relationship just to make it easier to understand. We also need to make sure that the data type matches. So actually, let me cancel out here and we'll select category and make sure we know what's going on. It looks like cat ID is number 4, 0. Okay, so we'll come back to NewProds, edit it, add a new column, cat ID. We'll make this number 4, 0, not null. And now for foreign keys, we're going to add a foreign key. The reference schema is HR. The reference table now is category. The reference constraint, or the primary key side in that table, is called category_PK. And then we verify what Oracle is telling us here, that we're matching the cat ID column in the NewProds table to the cat ID column in the category table. And what that's going to mean in practice is, as we're adding new data to the products table, whenever we reference a category, it's going to have to exist in the category table. You create a referential integrity link between those tables. All right, so let's OK that out. And let's look at the data in category really quickly to make sure we know what's there. It looks like there's a cat2 and a cat3. For a cat name, the cat IDs are 1 and 2. So keep that in mind. Let's come over to NewProds and let's add a few rows in. We'll add ID 100. The product name is Foo. The price is $45. And we'll say the cat ID is 2. Add another row. We'll say the ID is 200. The product name is Bar. Product price is $99. And let's put in cat ID of 4. Let's hit commit. And it gives us in our log down below, Aura 2291 integrity constraint violated, parent key not found. So it's not going to accept that. One error saving changes to HR. So if we run a select statement against NewProds, we've got some problems to take care of. So let's change this cat ID to something that's valid. Commit those changes. Commit was successful here. It gives us our insert syntax. So if we run that select again, sure enough, it comes back with both rows. If we truncate the table, NewProds, as long as we have privileges to do that, and then run a select, there's nothing there. If we drop the table, notice that there was no, are you sure you want to do this? Select statement now says, Aura 942 table or view does not exist. Let's now have a closer look at the SQL behind constraints, looking at the foreign key constraint and the check constraint this time. I've selected the job history table from the HR schema and in SQL Developer navigated to the SQL tab. Let's dismiss this to give us a little bit more room. Now you'll notice that the SQL here is a lot more verbose than what you would probably actually type in your script files. It's very formal syntax, and as we said before, you can place your constraints either in line right next to the column name in the column declaration, or you can add them down here after the last comma, after the last column. So you notice that on this job history table, we have a constraint called jhistDateInterval that's of the check variety, and this ensures that the end date is greater than the start date. So this is just to make sure you don't put an invalid date in. We also have primary key constraint added to the employee ID column, and then we have 3 foreign key constraints. I wanted to show you how this looked in SQL. Earlier, of course, I misspoke and said there was no foreign key keyword. Of course there is. The references is what ties the foreign key column in this table to the matching primary key column in a destination table. So first we have foreign key, where we pass in the name of the local column, and then the references clause that points to the related table that has the primary key. So we have a references to the department ID column in the departments table, and the employee ID column in the employees table, and the job ID and jobs. Quite a bit of relationships tying into the job history table. Let's now finish this demo. I'm going to select the T1 table that we used in an earlier nugget. Actually, instead of selecting it, I'm going to right-click it and edit the table. What I want to do is add a column. I'll call it cost. We'll use the number data type, precision of 5, and we're going to add a check constraint. Click Add, such that the cost is greater than 0. Simple as that. Very simple. We want to make sure that nobody puts in a negative cost into that table. Let's go to the Data tab now, add a new row, give it ID 11. The location we'll say is Las Vegas. The cost, 200. Add another row, ID of 12, location, Chicago, cost -1, and let's commit the change. Sure enough, we get an error or a 2290 check constraint violated, and then it points out where in our SQL. So our check constraint is working just fine, and that change will not be recorded in the base table. The final thing I want to show as a learning tool is if we right-click a table, you see that in the flyout menu, there's a lot we can do. If we go to table, we can rename the table, drop it, truncate it, comment it, etc. You can work on columns to add a column, drop a column, manipulate constraints, indexes, privileges. Really, SQL Developer is a tremendous learning tool as well as an automation tool. Now, for the purposes of your exam, you don't want to limit all of your studying to SQL Developer for sure, because you need to understand the SQL that's behind these various operations. But the reason I spent so much time in this nugget on SQL Developer is that really the subject matter called for it, and as long as you understand the SQL behind the scenes, I see nothing wrong with helping you automate your work. Using DDL Review, we started this nugget by understanding the main database objects. I hope now that you have a lot more clarity than you might have had prior to starting this nugget, thinking, oh, well, great. Now I'm really able to pull together what we've learned in the previous 10 or so nuggets, and I have a pretty nice framework of reference from which to work. I hope that you can say that. You also know how to use the create, alter, and drop statements to create and manage tables. You understand all of the theoretical underpinnings of the table, how and why they're used. You also understand how to protect tables by selecting appropriate data types and integrity constraints. I hope that this has been informative for you, and I'd like to thank you for viewing.